Okay, so we're back with our friend home market value data set. This time I'm going to show you how to implement it in the data analysis toolpack and how to interpret some of the results. So I think we're au fait with the data analysis toolpack. Go to data analysis, and then click regression. Now, let's just set this up. It's kind of pretty self-explanatory. So this is the Y. Select the Y. Then select the X and drag. Now we included the labels square feet and market value. So we want to click the labels because the first item is a label. We want to fit the standard regression model, i.e. there's going to be a constant or intercept, so we leave that unchecked. And we're going to include some confidence estimates. We're going to leave the residuals until the next example. And where do we want the output? Let's just stick it a little bit to the right. We'll put it E2. Okay. So the first thing, and I'll go through the most important things, is the R squared, and I think I've mentioned this is the variation in the Y accounted for by the X, so the variation accounted for by the regression. If the regression is perfect, all the points are in a straight line, then it's going to be 1. If there's absolutely no pattern whatsoever, it's going to be 0. The correlation, R squared is the square of the correlation. So the correlation is, this is the square root of F5 is the square root of F6. We could just actually check that if you don't believe me. So the square root of that is the one in the step before. And as I said, the adjusted R squared, this is if we're for comparing models, and this accounts for the number of parameters. So we maybe want to see if we want to compare regression with just square feet versus regression with house age and square feet, we'd want to compare the adjusted R squared rather than the R squared. For the moment, we're not going to worry about the ANOVA. We'll talk about that in multiple regression. But we also have a few t-tests. So just give me a second and I will just kind of clip the video. Okay, or I'll clip the video, clip the screen. So we have a hypothesis test, and we're just going to stick with the two-tailed version here, because that's the one that's kind of mentioned in the book. It doesn't worry with a one-tailed version. But we're going to do a two-tailed test. And the null hypothesis is that my beta 1 is equal to 0. And my alternative hypothesis is the beta 1 is not equal to 0. So the beta, the beta 0 and beta 1, these are the population values. And our sample parameters, this is what, I had an example I gave in my first video. So depending on your textbook, this is either B0, B1, or beta. I prefer this one, beta hat 0 and beta hat 1. These are basically the same thing. These are the sample values. And we have a t-statistic. Which is equal, the t is basically, and I'm not going to test the formula for this, divided by the standard error, which again, particularly when we do multiple regression, this requires a little bit of knowledge of sum of squares and linear algebra. So we're just going to focus on the computational interpretation. Now for the test, we're going to reject H0 if the absolute value of my t is greater than t. It's a two-tailed test, so as before, t alpha over 2, where this is my type 1 error. And let's draw this as a standard t-test. So in the middle, this is my t is 0. And this is where my sample statistic is also, if you look at this, if t is 0, my sample statistic is 0. So there's no evidence here that, it's the beta 1 is different from 0. And again, as it gets bigger or smaller, we get more and more evidence that this is not equal to 0. Until we reach these rejection points. And this is just because it's a two-tail, we divide the type 1 error by 2. So that's going to be alpha over 2. This is going to be t alpha minus t alpha over 2, t alpha over 2. And basically, we just reject if the absolute value of t, incorporating both of these, is greater than t alpha over 2. So if my t alpha over 2 was minus 2 and plus 2, then my t was minus 3 or plus 3, then by setting the absolute value, we'd say, yes, we're going to reject. And we can also reject, let's get a different color. Remember, the p-value is the area more extreme than, say my t was here. My p-value is the area more extreme than my statistic. And as this value gets smaller, we get to the critical region until we eventually reject. So it's equivalent to, say, reject H0 if my p is less than alpha. So this is the easy way of doing it because it's consistent with all the other statistical tests. And here, we're now very important, the p-value we're testing is for the B0, sorry, the B1. Try to fool you there for a minute. So we're not worried about the intercept. That's what we're testing, We're not testing where the intercept is. We're not testing, how far down this axis is. We're testing, is the regression kind of meaningful? So is it this kind of straight line in a cloud? That's going to be B1 equals 0. Or is it going to be, some sort of slope here where B1 is not equal to 0? So again, reject if your test statistic, or reject H0 if P is less than alpha. We see here, remember, 3.8, E minus 8 is 3.8 times 10 to the minus 8. This is a really, really small number. It's like 0.0000, etc. So in this case, we reject H0. We'll say, okay, my p-value is 0.000000 is less than my alpha if my alpha is 0.05. So we're going to reject H0. So say, for example, here my alpha was going to be 0.05. I'm going to say, my type 1 error, I'm going to say, okay, my p is 0.000 to 3 decimal places is less than 0.05, so reject H0. Okay, and that's it. And we're going to do the same thing in the next video, but focus on some of the kind of residual analysis. Okay, so I just wanted to add one little last thing, and that was the confidence interval. Now, interestingly, we actually get two confidence intervals here. We get the 95 and the 95 again. I think that's because it does one by default, and the other one is the one that's specified. Now, just to note, these confidence intervals are for the regression coefficients. They're not for individual items. So this would not be, for example, a confidence interval. Sorry, a confidence interval for an individual house. This is purely for the actual regression line. So we can see that the confidence interval for the slope is between 24.5 and 45.5. And the confidence interval for the intercept is between 15,000 and nearly 50,000. And we'll get these wide ranges if we only have a small data set like this. If we had 1,000 houses in our data set, we'd have much narrower confidence intervals. The other thing to note is, our statistical test that we do here to get the p-value is to test whether or not the coefficient is 0. So we could do like almost a virtual hypothesis test. Let me just demonstrate here. So we could, for example, have H0. Oh, we're on the blue still. Beta 1 equals 30. So this is the slope coefficient, which of course we interpret as the increase in market value for every additional square foot. And we can say here, if we're in the confidence interval, we don't have enough evidence that it's not 30, so we'd say fail to reject. As in confidence interval. Because for a t-test, you probably did this in your stats class, a two-tailed hypothesis test is pretty much identical to a confidence interval and checking whether your null hypothesis value is within the confidence interval. Okay, so that was just a little kind of additional piece of information.